Now the question is, does u of xt satisfy the initial condition? Okay. And this I alluded to a little bit before, and actually it depends, right, on properties of f, right? And there's a few different possibilities, right? So first of all, you've had some course on Fourier series before. You've probably gone over this, but if f is piecewise smooth, right, then let's say it's C1, 0 to L, basically, except for a finite number of discontinuities, okay? So you could have, a jump discontinuity here. You could just poke a hole in the solution here and take another value here, right? I'm still going to be able to compute those integrals, right? But you would imagine that because I can poke holes in a function and it's not really going to change the integral, then it can't be that I'm always sure to satisfy f everywhere, right? It's going to be almost everywhere that my constructed function works. Why? Well, because sines are smooth functions, right? Now you can make, sort of these jump discontinuities with an infinite series of smooth functions, right? But as far as these holes in the function, right, there's no way to sort of, capture these because of the way that integration works, right? So essentially what we have is that this sum, right, n equals 1 up to infinity bn sine of n pi x over L, right, is going to be equal to 1/2 times the right limit. So I'll write it as y goes to x from above of f of y plus the limit as y goes to x from below of f of y, okay? It's going to be the average of those two, okay? And you can prove this using something called Dirichlet's theorem, okay? And this essentially is what's called pointwise convergence of your Fourier series to the function that you're trying to fit to or describe, okay? Another way of saying this, okay, is that for any epsilon greater than 0, x living in 0 to L, okay, fixed, there exists an m greater than 0 such that 1/2, okay, of the rightward limit to x and the leftward limit to x, basically the average of the left and rightward limits, minus a partial sum of sine of n pi x over L. The absolute value of that, or basically the magnitude of that difference, can be bounded from above by epsilon, okay? So if f of x is not equal to the average of its left and right limits, right, as you wouldn't have for a piecewise smooth function, okay, then f of x does not equal the Fourier series everywhere, okay? But, say it, almost everywhere, okay? On a point of measure 0, some, you know, some number of points that you have where those discontinuities are, okay? So, so do I need to say anything else about this? Oh, sorry. So this here, n is greater than or equal to m, right? So there's some, you know, m, and if I make the series long enough, essentially I can hit that bound on the difference between them. And the proof is in Shearer and Levy. So if you want to see that proof, you can see it there. Okay. Why do I say this? Well, because, you know, you may have an initial boundary value problem where you have like a step initial condition, right? Let's say that you have a heat equation, right? And essentially f of x is set up to be, so let's say this is 0 and this is L, and you initially are setting some interior region to be a certain temperature, and then you have a step down to the temperature over here, right? And so there's a jump discontinuity here, okay? Then all that's going to happen is that your Fourier series, right, at the jump discontinuity is just going to take on this point value here, okay? Moreover, if you have f of x here, and let's say that, you know, for whatever reason, you construct a function that looks like this, okay, then the Fourier series basically takes this value. Basically, the value that's in this hole here is going to be the value taken by your Fourier series, because that's going to be the left and right limits of your function here, okay? So fine, we know that. So
but physically that's not possible, right? Like for any quantity to have a completely different value at a particular point.
No, but I mean, you know, sometimes it is helpful to have jump discontinuities, but these just sort of point-wise holes in functions. I mean, yeah, it's hard to think of a physically relevant situation where you would necessarily need that. You know, except of course the delta distribution, but that's a whole nother animal. But yeah. So we want to talk about that case for now. Okay. All right. So that means, you know, at the worst, if we have a piecewise smooth function, then we can construct a Fourier series that sort of works everywhere except for the discontinuities. Okay. Let's look at another case where f is C1 everywhere. Okay. Then what we can say is f of x is equal to the sum from n equals 1 up to infinity bn sine of n pi x over L, okay, converges what's called uniformly, okay, in x, okay. And how do we define uniform convergence in x? Okay, well, again, we're gonna take one of these epsilon sum size conditions. And we can say that really for any upper bound that we want on the difference between our function and our Fourier series, okay, there exists an m greater than 0 such that for any x, okay, again, f of x minus, I'll write this down here so I have more room, So now instead of having to write the right and left limits, right, because of continuity, we know the right and left limits, right, are just going to be the function itself at that boundary, because at that point, because we have required that the function be C1, okay? So in this case, we can say that, well, f of x minus its Fourier series is going to be bounded from above by epsilon for any n greater than or equal to this n. So what does that say? Again, I can always take a partial series that's big enough that I get as much accuracy as we like, right? And of course, this says something about convergence, but if you think about numerical methods, things like spectral methods, right? A lot of what are called spectral methods for numerical PDEs really rely on representing functions according to a partial Fourier series, right? And what this means is that I can get as much accuracy as I like representing solutions with just a partial sum of a Fourier series. Because when you're doing this numerically, right, you can't ever really write down an infinite Fourier series, but you want to know that if you write down enough terms in your Fourier series, you'll get a good approximation of your PDE, and you'll get a good approximation of the functions that are solutions to your PDE, okay? So this is useful for that as well, okay? So the proof of this is in Shearer and Levy. I'll just leave it at that, okay? This is, yeah, this is maybe something that you came across in a prerequisite course, okay? I'm gonna say one more thing and then I'll stop, okay? If we go further, right, if f is actually C2 in 0 to L, okay, f of 0, f of L equals 0, okay, the proof is easier in this case. And essentially what I can show is that Bn is equal to 2 over L integral from 0 to L f of x sine of n pi x over L dx. I'm going to integrate by parts now. I'm actually going to integrate by parts twice. Here's my first integration by parts. I get L over n pi times 2 over L integral from 0 to L f prime cosine n pi x over L dx. Okay, let's do another integration by parts. I get a minus L over n pi, that whole thing squared, 2 over L integral from 0 to L f prime prime of x sine of n pi x over L dx, right? And so this implies, okay, that Bn, our coefficients, are equal to 2L pi squared, something that I'll call m prime prime, which is just going to be this m prime prime here, times 1 over n squared, right? So if I have this, okay, we can use what's called the Weierstrass M test to prove convergence of our sum. But the idea, I'll just say it, I won't go through Weierstrass M test because we're at end of time. I will put it in the recorded lecture. Notice that basically as n grows, right, n here, n squared is going to increase, right? So your infinite sum, your Fourier series, right, the terms in it are going to decay like n squared, okay? And what you probably remember from calculus, right, is when you have an infinite sum like this, convergence works out fine as long as the individual terms, right, scale like you know, n 1 over n squared or faster than that, right?
Doesn't that m prime prime depend on n? Was there some reason we were supposed to get rid of the n's in that expression?
Yeah. So because this, you know that f is C2, so this is fine. This is not unbounded. This is also a bounded function. So you can always
Oh,
bound this whole thing with just like a constant, right? So I should say bounded by m prime prime. So yeah, you're right, this depends on n, but you know what kind of animal sine of n pi x is, right? It's, you know, it has some maximum. You could always just take like the maximum of that, right? You could take the maximum of this, right? Because you know it's not going to be infinite because f is C2, and just you know, bound everything by a constant. So then you just have a constant times 1 over n squared. Okay, so that's the idea in this case, and then you can apply the what's called the Weierstrass M test, which I'll record that and put it in the lecture, the next lecture that I'm recording. Okay. So yeah, sorry we bled over a bit with time, but what did we learn today? Well, first of all, we just learned the method for identifying the coefficients of Fourier series solutions. I mean, in the case of the heat equation, initial boundary value problem. These ideas extend to inhomogeneous problems, other PDEs. We'll talk more about that. One of the key concepts that we saw today is that in order for everything to sort of work out nicely in terms of constructing these coefficients, we need completeness of our set of eigenfunctions, which means we can make any function that we like as long as it's, you know, C1 from our eigenfunctions. And if it's just, you know, something like L2, then you know, it'll be pointwise convergent. We need orthogonality. And so we'd like some general theory of when we're going to get completeness and orthogonality, and that's what Sturm-Liouville theory helps us with. And we showed that once we construct the solution, it satisfies the PDE, it satisfies the boundary conditions, and it'll satisfy our initial condition at least almost everywhere as long as we have a piecewise smooth function f. If it's smooth enough, then it should satisfy our initial condition everywhere. So this brings into focus what's called, like, you know, L2 convergence and different types of convergence that we'll talk more about as we, I think, in the next lecture. But that's it for today. Any questions before we wrap up? Okay. Sorry to go over a bit. If you do have questions about your exam, like I said, you can reach out to me by email. Sounds like there's already one typo for me to fix in the solutions. And then on Friday, I mean, as usual, we can just work a practice problem. If you have a particular practice problem you want to